Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind adjust the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. My contributions to computer science that made the news headlines in 1989 were these. I discovered how to record the fastest computer speeds and how to do so by computing across an ensemble of the slowest processors in the world. I discovered how to leapfrog from slowest processors to fastest computers. The fastest supercomputer in the world is the heavyweight champion of the computer world. Beyond the fastest supercomputer is an unknown field of knowledge or a place where chaos begs to be replaced with order, darkness by light, ugliness by beauty, and ignorance by knowledge. I discovered how to leapfrog from the slowest processors to the fastest computers, solving problems at the speed limit. I discovered how to solve the most compute-intensive problems in mathematics and science and solve them with the slowest processors. I discovered how to make the most with the least. The Eureka moment or high point of my parallel supercomputer quest for the fastest computer in the world occurred at 15 minutes after 8 in the morning of July 4, 1989 in Los Alamos, New Mexico, USA. And it occurred within my ensemble of the slowest 65,536 processors. In 1989, I was in the news for providing the quote-unquote final proof that supercomputing across millions of processors is not science fiction. In theory, mathematical predictions that were governed by a system of partial differential equations that encoded some laws of physics should be as reliable as a hammer. But in practice, it's a different story. The fastest computer in the world shortens the gap between theory and practice. In a world without the fastest computers, the solutions of the most compute-intensive mathematical problems, such as the simulation of long-term climate change, will be as approximate as a sketch instead of as exact as a photograph. The implication of my discovery of the first world's fastest computing executed across the world's slowest processors was far-reaching. My invention made the news headlines because the world's fastest computer is an enabling technology that enables us to discover new knowledge and unknown materials and create never before seen products. My contribution to computer science is this. I was in the news because I was the first person to use the slowest processors to discover the fastest computing and solve the most compute-intensive problems. To invent is to create something from nothing or make the fictional factual. The discovery is a time machine that takes us to the past to see a thing that pre-existed but remained unseen. The invention enables us to create our future. Genius is the ability to see what others saw as a rock and see it as a diamond. I achieved a milestone in the history of the computer. On July 4, 1989, the supercomputing community marked my milestone as the first time the world's fastest computer speed was recorded across the world's slowest processors. In supercomputing, the perennial question was how to discover the fastest speeds and use them to make the impossible to solve mathematical problems possible to solve. Before my discovery of the world's fastest computer, which occurred on July 4, 1989, how to solve the most compute-intensive mathematical problems wasn't known to any mathematician, wasn't taught in any mathematics course, and wasn't written in any mathematics textbook. Since 1974, my research quest was to discover how to harness the slowest processors and how to use them to solve the most compute-intensive problems at the fastest computer speed. In the 1970s and 80s, my theory of how to build the world's fastest computer and do so with standard parts, such as the world's slowest processors, was mocked, ridiculed, and dismissed as a beautiful theory that lacked experimental confirmation. The supercomputer was a technology that meandered across physics, mathematics, and computer science. And in the 1970s and 80s, supercomputing across processors was the beautiful thread that didn't fit into the larger weave, namely the world's fastest computer that now occupies the space of a soccer stadium, and it costs 40% more than the mile-long Second Niger Bridge in Nigeria. I'm well known, but not known well. It's not known well that I discovered the world's fastest computer and did so across the world's slowest processors. My discovery was the origin of the first supercomputer as we know the technology today. On the 4th of July 1989, I saw something that's a new supercomputer that nobody had seen before. Specifically, I saw how the slowest processors in the world could be utilized to solve the most compute-intensive problems in the world, and most importantly, solve them at the fastest computer speeds. I discovered the fastest computing and explained the technology to a 12-year-old writing a school essay on inventors as a quote-unquote solving up to 1 billion mathematical problems at once and across as many processors. In 1989, I was in the news because I solved a tough mathematical problem that was then considered impossible to solve. Furthermore, I solved 65,536 mathematical problems at once and across as many processors that work together as one coherent supercomputer. Likewise, I discovered how to solve the most compute-intensive problems at the frontiers of knowledge in mathematics, physics, and computer science. Not only that, I made the first direct measurement of the fastest computation ever recorded across an ensemble of the slowest processors in the world. After my invention, the fastest computers in the world are supercomputing across thousands or millions of processors. That radical shift from one processor to 1 million processors is the most significant fundamental change in the history of computer science. I began supercomputing on a machinery that I visualized as a processor. I began programming the fastest computers on June 20, 1974 in Corvallis, Oregon, USA. In 1974, the prevailing dogma was that recording the world's fastest speed in computing and doing so across the world's slowest processors will forever remain in the realm of science fiction, and it remains a colossal waste of time. In 1989, I was in the news because I proved that supercomputer scientists who believed in serial computing were wrong. I did so by discovering how to solve the most compute-intensive problems in physics and how to solve them so that a time to solution of 30,000 years will be reduced to a time to solution of 1 day. My discovery is a new way of looking at the supercomputer. That discovery marked the date of birth of the first supercomputer as it's known today and as it's expected to be known tomorrow. Processing across the slowest processors is the lodestar technology that makes the computer faster and makes the supercomputer fastest. The partial differential equation is the mathematician's stepping stone that enabled the physicists to answer otherwise unanswerable questions. The global climate model that was used to foresee climate change derived its answers from the laws of physics that were embodied into the governing partial differential equations at the frontier of calculus. The second law of motion of physics breathes fire into the trillions upon trillions of my interlocking partial difference equations of computational linear algebra, and did so to set millions of processors on fire and to add a new meaning to the ancient Pythagorean belief that nature was numbers. My invention opened the door to how to solve compute-intensive problems and solve them across an ensemble of millions of processors, and solve them when the governing system of equations of algebra has its non-zero entries only along its diagonal. I invented how to solve many of the most compute-intensive problems arising in engineering and medicine, and solved them in parallel, and invented how to solve them across an ensemble of 65,536 self-contained coupled processors. The 65,536 simultaneously sent and synchronously received emails fired from as many processors as bullets out of my eyes that were coming from 2 raised to the power 16 processors in a 16-dimensional hyperspace. My contributions to mathematics were these. I changed the way we solve compute-intensive mathematical problems. In their old way, they solved such problems with only one isolated processor that wasn't a member of an ensemble of processors. Or conversely, within only one isolated computer that wasn't a member of an ensemble of computers. In my new way, we solved compute-intensive problems across millions of processors or across millions of computers. My contributions to the science and technology that I used to discover and recover crude oil and natural gas were these. I discovered how to harness the millions of processors that powers the world's fastest computers and how to use them as one coherent machinery that emulates a super fast processor that's 1 million times faster than a single processor solving the same mathematical problem alone. One of the most difficult problems in physics was to accurately compute the flows of crude oil and natural gas flowing from water injection wells to nearby producing wells. By making the news headlines in 1989, my invention changed the way we execute mathematical calculations in the largest scale computational physics. And it changed how mathematicians solve the most compute-intensive and mathematical problems, such as those arising in fluid dynamics. And it changed how mathematicians solve them in parallel or in tandem, and solve them by distributing them across an ensemble of coupled processors instead of solving them in sequence or solving them only within one isolated processor that was not a member of an ensemble of processors. An example of the most vexing problem in physics is to foresee previously unforeseeable global warming. General circulation modeling is one of the most challenging problems in computational physics. Fluid dynamics across the Earth's subsurface gives rise to one of the most compute-intensive problems that often arise in algebra, such as the high-fidelity petroleum reservoir simulators that must be used to recover otherwise unrecoverable crude oil and natural gas. The reservoir simulation of the subterranean motions of oil and gas is one of the hardest mathematical problems. In Nigeria, the toughest or the most compute-intensive physics problems arise as trillions of equations of algebra that must be solved as a precondition to recovering crude oil and natural gas from the Niger Delta oil fields. In physics, the so-called Grand Challenge is defined as the field's most compute-intensive and most important problem. That compute-intensive problem is the accurate solution of an initial boundary value problem that's governed by a system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations. The later equations encode some laws of physics that include the second law of motion. These laws are defined in physics textbooks and govern the motions of the oceans and atmospheres that enshroud the Earth. This system of partial differential equations is used to forecast changes in oceanic and atmospheric motions and forecast the changes in temperatures that define the global warming of the air and moisture within the Earth's atmosphere and the sea level rise in the oceans. Analogous partial differential equations are also used to hindcast or reforecast the changes in the motions of crude oil, injected water, and natural gas that were flowing inside a producing oil field that's the size of Lagos, a city of 20 million Nigerians. The typical oil field is a porous medium that's on the average 6,000 feet or 1.83 kilometers deep. Calculus is the most powerful technique in mathematics and physics. Calculus was discovered 330 years ago, but it was discovered as a textbook problem that's posed and solved for mathematics classes and on the blackboard. The body of knowledge of calculus grew over 3 centuries and 3 decades, with the first partial differential equation invented in 1746. However, the phrase partial differential equation was first used in 1845 and a century after it was invented. That body of mathematical knowledge grew over the years to become the backbone of computational physics. The partial differential equation is the most recurring decimal in the most compute-intensive problems. Such grand challenge problems are solved across the up to 1 billion processors that outline and define the world's fastest computer that now occupies the space of a soccer field. Unlike the ordinary differential equation that's defined by its single variable functions and their derivatives, the partial differential equation is defined by its unknown multivariable functions and their partial derivatives. My contributions to the partial differential equation beyond the frontier of calculus were these. In the early 1980s, and while in College Park, Maryland, I invented 36 partial derivatives of unknown multivariable functions. Computational geophysical fluid dynamics engineers could use my contributions to mathematics to more accurately forecast the changes in the motions of crude oil and natural gas that are pushed from a pumping well to nearby producing wells. And we are within a producing oil field that's up to 7.7 miles or 12.4 kilometers deep and up to twice the size of Anambra State of Nigeria. I discovered that the system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations that the petroleum industry used to discover and recover crude oil and natural gas. We are missing 36 partial derivative terms. Those mathematical terms were needed to balance the system of 9 coupled, nonlinear, time-dependent, and three-dimensional partial differential equations that are used in the energy and geoscience industries. Who needs a supercomputer? The initial boundary value problems governed by my new mathematics or partial differential equations had no analytical or exact solutions. For that reason, those equations had to be discretized and roughly solved across millions of processors under the hood of the world's fastest computer. Every oil company must use a supercomputer to simulate the perfect operational strategies for recovering crude oil and natural gas. Petroleum reservoirs simulated across millions of processors is standard operating procedure that must be used to extract crude oil and natural gas from the 159 producing oil fields in Nigeria, as well as the 65,000 producing oil fields around the world. It should not come as a surprise that the energy and geoscience industries bought 1 in 10 supercomputers, and that the supercomputer industry has a market value of $45 billion a year. Why are the 9 Philip Emeagwali's equations important? My contributions to the mathematical knowledge that's used to recover crude oil and natural gas were these. I corrected the serious mathematical errors made by geologists and physicists and made during their mathematization of Darcy's law. Darcy's law was formulated in 1856 and later enshrined into every physics textbook on porous media flows. That invention of 36 partial derivative terms is my contribution to the calculus of multi-phase fluids which flow under the surface of the earth, specifically 3-phased flows of crude oil, injected water, and natural gas flowing along 3 dimensions and across porous media that were both heterogeneous and anisotropic. My contributions were toward the applications of mathematics and toward using my new knowledge and the world's fastest computer technology to discover and recover the most crude oil and natural gas buried in the 65,000 producing oil fields of the world. Without the supercomputer that's powered by millions of processors, a significant amount of crude oil and natural gas would remain undiscovered, undiscoverable, and unrecoverable. In the 1980s, the petroleum reservoir that I simulated across my 65,536 processors served as my concrete platform and as my metaphor for all initial boundary value mathematical problems, from those which govern the traffic models of Main Street to those which govern the financial models on Wall Street, to those govern the massively parallel processed computational fluid dynamics codes that I investigated for 4.5 decades following the late 1970s. What's my answer to the most challenging question in computer science? I invented how to solve the most compute-intensive problems at the intersection of new mathematics, new physics, and new computer science, and how to solve them by sending and receiving up to 1 billion computer codes Each computer code represents an initial boundary value problem that must send and receive data or intermediate answers to and from nearest neighboring domains. I invented how to do so across a new internet or across a new global network of processors that communicates and computes together as one seamless, coherent, and gigantic supercomputer. That's the first supercomputer, as we know the world's fastest computer today. My world's fastest computer is not a regular computer in and of itself. It's a new internet in reality. I made my invention by sending and receiving the internal boundary conditions after each time step of my discretized initial boundary value problem. And by doing both across a new internet that I visualized as my new hyperbole supercomputer, and as my new global network of 1,048,576 regular and short email wires, which were equal distances apart, and which interconnected my ensemble of 65,536 off-the-shelf self-contained processors, and interconnected them to create my new spherical island of processors. That's a new internet. Back from 1922 through 1989, harnessing 64,000 human computers, or as many processors, existed only in the realm of science fiction. Since my discovery of July 4, 1989, executing the world's fastest computing, and doing so across ordinary processors, has enabled us to incorporate previously unimaginable points of data. We did so to make groundbreaking discoveries in science, engineering, and medicine. The world's fastest computers are used to know if a new cancer treatment holds any promise, or if an untested scientific theory is valid. The world's fastest computers are used to deepen our understanding of the cosmos and know our place within the cosmos. The reason my scientific discovery of the world's fastest computing across the world's slowest processors was cover stories of top scientific publications was that it was new knowledge that opened doors into an undiscovered territory in advanced calculus, and that it opened doors into an undiscovered territory in compute-intensive algebra, and it opened doors into the unknown world where the fastest computers exist. New calculus, when discretized, led me to new algebra and led me to faster mathematical computations that were at the granite core of my scientific discovery. That discovery opened doors into the undiscovered territory of the first world's fastest computing across the world's slowest processors. In 1989, I was in the news because I was the first person to observe the world's fastest computation across processors instead of within one super fast processor. My world record calculation made the news because it was across an ensemble of the world's slowest processors and across an internet that's a global network of those processors. That first parallel supercomputer is the precursor to the world's fastest computer of today that could become the computer of tomorrow. My mathematical grand challenge was to figure out how to harness a new internet that's a new global network of up to 1 binary billion processors that shared nothing and were equal distances apart. My contributions to mathematics were these. I figured out how to harness that new internet and how to use its processors to solve a complicated system of time-dependent and nonlinear partial differential equations arising in fluid dynamics and calculus. For the past 2 centuries, the partial differential equation was the hottest topic in mathematical research. It's both difficult and important. For those reasons, 9 in 10 supercomputer circles are devoted to solving partial differential equations. It's the reason mathematics, physics, and computer science mutually reinforce each other. Those partial differential equations are encoded in some laws of physics as prior information and therefore can be used for physics-informed simulations. Such computational physics models range from high-stake climate models to the spread of contagious viruses that might occur during a once-in-a-century global pandemic, such as the spread of COVID-19. To solve the most difficult mathematical problems in computer science and solve them across processors demanded that I reduce those differential equations of calculus to an equivalent system of difference equations of algebra. On July 4, 1989, the system of equations of computational linear algebra, which I solved across my ensemble of 65,536 processors, were too bulky and sprawling to be scribbled across all the blackboards on this earth. As a research mathematician, I started in Onitsha, Nigeria, investigating the Pythagorean triplets, defined as 3 positive integers, a, b, and c, such that a squared plus b squared equals c squared. I did so after the 30-month-long Nigerian Civil War was over. When the war ended on January 15, 1970, 1 in 15 Biafrans had died. 1 million children and the elderly died from hunger and starvation. I was a 12-year-old refugee in Biafra, the breakaway southeastern region of Nigeria. My refugee camps were in Ogidi, Oka, Oketiti, Oba, Ndoni, and Fege quarters of Onitsha, Biafra. As a mathematician searching for new calculus and new algebra, I came of age in supercomputing in the mid-1970s in Corvallis, Oregon. And as a mathematician in the early 1980s in College Park, Maryland, my obligation was to invent new mathematics and then use my new knowledge as a vehicle for discovering new physics and for inventing a new computer, a new supercomputer, and a new internet. and for creating new vocabularies and discovering new sciences that must follow: new calculus, new computer, and a new internet. Why must Africa always be at the frontier of human knowledge? If it's impossible to create a literary renaissance in Africa, and do so because of the continent's low literacy, it will then be harder to create a scientific renaissance in Africa, and do so because its low numeracy is far more daunting than its low literacy. Mathematics can only foster where numeracy is high. The lack of deep understanding of the partial differential equations of calculus that were employed to construct large-scale supercomputer models of producing oil fields is one reason European and American oil companies are paid 40% royalty to extract crude oil and natural gas, and do so from the 159 producing fields of Nigeria and through the 1,481 oil wells in Nigeria. The pyramids of Giza are testaments that Africa was once at the frontier of human knowledge. The pyramids that stand today were built 4,000 years ago, built in Africa by Africans, and built in the millennia at the forefront of human knowledge was in Africa. Africa will forever remain the least developed region if it continues to consume technologies rather than produce technologies. For 43 years following 1946, computers got smaller and faster. After 1989, supercomputers got bigger and became a billion times faster. They are defined and outlined by up to 10.65 million smaller and faster processors. The first world's fastest computing across billions of coupled processors that shared nothing is the most significant measurable increase in the supercomputer speed that has occurred since the programmable computer was invented in 1946. My discovery of the world's fastest computing is called parallel processing. It occurred at 15 minutes after 8 in the morning of July 4, 1989. Supercomputing across processors led to the acceptance of the new technological reality. My invention or new knowledge was this: the slowest processors could be used to compute faster than the singular custom manufactured fastest processor. Such an ensemble of processors are now used to solve the most compute-intensive problems in mathematics and science. Parallel processing was the seminal discovery in supercomputing. Parallel processing was how the fastest supercomputer was invented. I was in the news for my discovery of the first world's fastest computing across the slowest processors in the world. My discovery occurred in Los Alamos, New Mexico, USA. I jumped in joy because I was the first person to discover that the 65,536 slowest processors in the world can be used to solve the most compute-intensive mathematical problems in the world. Working together, an ensemble of the slowest processors can be utilized to address the world's biggest challenges and solve them faster than the fastest supercomputer in the world could. My scientific discovery changed the way we look at the supercomputer and changed it from the supercomputer powered by one processor to the supercomputer powered by up to 1 billion self-contained coupled processors. That supercomputer discovery put me in the news headlines in 1989. It's the reason I'm the subject of school essays on inventors. Those news headlines from my world's fastest computing that I executed across the slowest processors in the world helped capture the public imagination. Those news headlines helped to garner political support for the new supercomputer technology that can now be harnessed and used to solve the most compute-intensive problems. My quest was to discover the supercomputer solution of the world's most compute-intensive problems. Such difficult mathematical problems arise at the frontiers of knowledge in mathematics, science, and medicine. My quest was to discover how to harness the slowest processors in the world, and use them to solve the most compute-intensive problems in the world, and solve such problems at the fastest speeds in the world. As a mathematician searching for never-before-seen equations of calculus and algebra, and who came of age in the 1970s, and who worked at the frontier of the most compute-intensive fluid dynamics, I flaunted my uncompromising theories, and I theorized about sending and receiving emailed codes and sending them across a new internet that's a new supercomputer in reality. As my act of protest was against the racism I experienced in the 1970s and 80s, I pursued an unorthodox line of research called parallel supercomputing. In 1982, my supercomputer discovery was rejected. It was dismissed as science fiction. For those reasons, I then expected supercomputing across processors to be always rejected. I discovered that the 1 billion slowest processors in the world can be fused via emails and used to emulate one seamless, coherent, and gigantic entity. This new machine is equivalent to a high-speed processor that's 1 billion times faster. It redefines the fastest supercomputer. Parallel supercomputing is new mathematical knowledge that came of age on July 4, 1989, the day I discovered that it's faster than serial or vector computing. I established the science of fastest computing across the 7 million processors. Supercomputing is derived from parallel processing. Parallel supercomputing is my contribution to mathematical knowledge and is the invention and milestone that changed the way the modern mathematician solves his or her most compute-intensive problems and addresses some of the world's biggest challenges. The supercomputer is where the supercomputer is the scientist's best friend. Developing the world's fastest computer is the most expensive project in computer science. A recurring question in school essays is this: what did Philip Emeagwali contribute to science? Imagine a huge multi-volume textbook that contains all that's known in mathematics or physics or computer science. To make a simple discovery is to add one new sentence to that textbook. But to make a groundbreaking discovery that opened the door to a new field of knowledge is like adding a new volume to that book of knowledge. My discovery of the first world's fastest computing across the world's slowest processors made the news headlines in 1989. I was in the news because my discovery was a new volume that was added to the body of knowledge of mathematics, physics, and computer science. If my discovery, namely the world's fastest computing across millions of processors, is deleted from scientific knowledge, we will not have the fastest computers in the world. I was born in 1954 in the British West African colony of Nigeria. At age 19, I emigrated to the USA. In 1989, I was in the news for inventing the technology of using millions of processors as one coherent unit that's the world's fastest computer. As an aside, the earliest use of a computing aid to compute faster was in Africa. The Lebombo bone is the oldest mathematical instrument. It's 35,000 years old. The Lebombo bone was discovered in the Lebombo Mountains of Swaziland, Africa. Mathematics originated in Africa. For thousands of years, our human ancestors counted on their fingers and on their toes. 3,000 years ago, alternative ways of counting that used computing aids such as the counting board and the abacus were invented. Those alternative ways were paradigm shifts in the history of computing. The fastest computing across millions of processors changed the logic of sequential computing. That logic changed from solving one mathematical problem at a time to solving a million problems at once or in parallel. That fundamental change was this: the sequential thought processes of yesterday were replaced with the parallel thought processes of today. Like a storm at sea, supercomputing across a million coupled processors has brutally pushed computer science in a new direction and created new fields of study across mathematics and science. Computing in parallel changed the course of science and technology. In computer science, the most important questions are these: how do we achieve the fastest computer speeds that now exist only in the realm of science fiction? How do we harness those new world record speeds and use them to solve the most compute-intensive problems that are now impossible to solve? And how do we use those speeds to solve societal problems that bring value to life? These quintessential questions of computer science can be rephrased. For a small price and many processors, what is the upper limit on the supercomputer's speed? At 8:15 in the morning in Los Alamos, New Mexico, USA, on Tuesday, the 4th of July, 1989, I made the first measurement of the world's fastest computation ever recorded across an ensemble of the slowest processors in the world. My scientific discovery is an alternative way of looking at the world's fastest computers. My discovery of the fastest computing across the slowest processors made the news headlines. My contribution was the first time that an ensemble of the slowest processors in the world computed faster than the fastest processor in the world. In 1989, I was in the news because I discovered how a billion processors can coordinate and work together and do both to solve one compute-intensive problem, such as modeling climate changes across the centuries. I discovered how to harness millions of processors and do so to solve one compute-intensive and time-consuming problem which otherwise would be impossible to solve. My discovery of how to use standard parts called processors to build the world's fastest computers occurred on the 4th of July 1989. My discovery was summarized in many trade publications and mentioned in the June 20, 1990 issue of the Wall Street Journal. My signature discovery was that millions of processors could be harnessed as one seamless, coherent, and gigantic unit. That's the world's fastest computer. My discovery made the news headlines because the world's fastest computer, that's powered by 1 million processors, was previously dismissed and abandoned by the leaders of thought in supercomputing. The technology was then rejected by their followers, who offhandedly dismissed the parallel supercomputer as science fiction and as a tremendous waste of everybody's time. To put my discovery in perspective, the computing power of today's smartphones is about the same as the processing power of the supercomputer that helped send men to the moon. That first moon landing occurred on July 20, 1969. That was about the date I went to the Biafran side of the Oguta War front of the Nigerian Civil War. I went to the Biafran war front as a conscripted 14-year-old soldier. A month before my arrival at that Oguta war front, the Nigerian army had outmanned and outgunned the Biafran army by 4-1 and killed 500 Biafran soldiers. My 20-year journey to the frontier of knowledge of the fastest computer was from the war front to the science front. In 1989, it made the news headlines that an African supercomputer genius in the USA had won the highest award in supercomputing. Computer scientists rank that award as the Nobel Prize of supercomputing. I was the African supercomputer scientist that was in the news in 1989. I won that award for discovering that the supercomputer that incorporated 1 billion processors can yield the processing power of 1 billion processors or of as many computers. My supercomputer discovery made the news headlines in 1989. It remains the subject of inventor reports in schools. The reason was that I was the first person to execute the world's fastest computer speed and record it with the slowest processors and solve the most compute-intensive problems. That supercomputer discovery was considered the most significant breakthrough in mathematics, physics, and computer science. My world's fastest computer speed of July 4, 1989 was a supercomputer milestone. It was the largest speed increase in computer science. My scientific discovery that the fastest computer can be built with the slowest processors changed the way we look at the supercomputer. Before my discovery, the most powerful supercomputer in the world was powered by at most one custom-made vector processor. After my discovery, the most powerful supercomputer in the world was powered by up to 10.65 million processors. In an email, a 12-year-old writing the biographies of famous computer pioneers and their contributions to the development of the computer asked me, how is the discovery of the world's fastest computing used? The energy and geoscience industries bought 1 in 10 supercomputers and used them to pinpoint oil deposits. Supercomputing across billions of processors is the $45 billion a year high-performance computing technology that's used to recover crude oil from the 65,000 oil fields of the world and used to simulate the spread of contagious viruses during a once-in-a-century global pandemic. Saudi Arabia classified the fastest supercomputer simulations of their oil fields as a state secret. In my lectures to the leading mathematicians and physicists of the 1970s and 80s, I explained that the open mathematical question was this: can mathematicians solve the most compute-intensive problems, such as simulating the flows of crude oil, injected water, and natural gas that were buried up to 7.7 miles or 12.4 kilometers deep and within an oil-producing field that's almost twice the size of the state of Anambra, Nigeria? And can mathematicians handcast those fluid flows across a new internet that's a new global network of up to 1 billion off-the-shelf processors? Each processor had its dedicated memory and shared nothing. My contributions to computer science were these. I discovered that the slowest processors in the world can be used to manufacture the fastest computers in the world and solve the most compute-intensive problems in the world. I discovered how to match mathematics to metals and do so to produce the fastest computers from the slowest processors. Since 1989, I'm the subject of school essays on inventors because I invented the first and fastest supercomputing as it's known today. On the day before my invention of July 4, 1989, the fastest computer was powered by one processor. On the day of my discovery, the fastest computer was powered by the slowest 65,536 processors in the world. On the day of my discovery, a compute-intensive problem that formerly took 65,536 days or 180 years to solve within one processor took only 1 day to solve across my ensemble of 64 binary thousand processors. I discovered how to harness the total and maximum supercomputer power of my coupled ensemble of the 2 raised to power 16 slowest processors in the world. Those off-the-shelf processors were designed for a mainstream market rather than for supercomputing, and were manufactured in large numbers and at a lower price. At computer science conferences of the 1970s and 80s, mathematicians and physicists argued that parallel processing is a beautiful theory that lacked experimental confirmation. After my discovery of July 4, 1989, computer scientists can no longer mock and ridicule parallel supercomputing as a beautiful theory that lacks experimental confirmation. Since counting is as old as humanity, parallel supercomputing could be around as long as the river flows and the grass grows. I'm a dreamer who dreamt science fiction as non-fiction. I expanded the story of science to become a part of that story and the witness. What does the world's fastest computer look like? The computing discovery that I recorded during my email experiments of July 4, 1989 provided the designers of the world's fastest computer with a crucial insight, namely that the most compute-intensive problems can be solved across an ensemble of millions of off-the-shelf processors. Each processor was self-contained and shared nothing, but was in dialogue with its nearest neighboring processors. That insight changed the way the world's fastest computer looks. The supercomputer of July 4, 1989 and earlier was the size of your refrigerator. The supercomputer of today occupies the space of a soccer field, consumes as much electricity as a small American town, and it costs as much as the budget of a small African nation. That change in the way the supercomputer looks and its cost is in part my contribution to computer science. My invention made supercomputing across ordinary processors the new normal and relegated the fastest supercomputers to computer museums. The invention of the first world's fastest computing across 1 million processors is the most significant fundamental change in computer history. Parallel supercomputing is computing's defining technical achievement. The car of today has 1 engine and 4 tires, just as it had a century ago. By comparison, the state-of-the-art supercomputer of today is powered by 10.65 million processors instead of the one processor that powered it before my discovery of July 4, 1989. The progress achieved in supercomputer technology is akin to completing in one day an intergalactic outer space travel that might have taken 300 centuries if the same trip started in 1989. I was the first person to discover that parallel processing across the slowest processors in the world is faster than serial computing on the fastest supercomputer in the world. That discovery enabled me to carve out supercomputing across the slowest processors and understand the new technology as the new window through which we can look with fresh eyes the frontiers of knowledge of the fields of computer science, mathematics, and physics. We use the state-of-the-art supercomputers to see a new horizon and dream of inventing a faster supercomputer, such as the quantum supercomputer. I was asked, why are you called the father of the internet? I'm the only father of the internet that invented an internet. The idea that suddenly the internet was invented in the 1970s doesn't ring true. Philip Emeagwali is the first name Google suggests for the search term, father of the internet. In 1974, I was the first person to sketch a new internet. My sketch evolved over the subsequent 15 years and can be seen in Google image search. My new internet was a new global network of computers. My new internet emulated one seamless, coherent, and gigantic supercomputer. My new internet made the news headlines because it materialized on July 4, 1989, as the world's fastest computer. That new internet was a significant change from a science fiction story that was published on February 1, 1922. That fiction introduced a paradigm of 64,000 human computers, quote unquote, racing the weather for the entire Earth. That science fiction story of 1922 inspired my supercomputing theory of 1974. I theorized as many computers forecasting the weather around the entire Earth. My theory of 1974 led to my scientific discovery and experimental confirmation that occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989 in Los Alamos, New Mexico, USA. I upgraded parallel supercomputing from fiction to fact. My original inspiration was to invent a new technology, namely a small copy of the internet that emulates a new supercomputer to be used to solve the most compute-intensive problems. I discovered how to solve the hardest problems and solve them across my small copy of the internet. My internet was a new global network of 64 binary thousand processors. Each processor within my ensemble operated its operating system. Each processor had its dedicated memory that shared nothing. Those identical processors were married together by 1,048,576 identical email wires and married together as one seamless, coherent, and gigantic unit. That's a new supercomputer that encircles the globe and does so in the way the internet encircles the earth. My ensemble of 2 raised to power 16 processors encircle the globe in a 16-dimensional hyperspace. I became the most searched for, quote unquote, father of the internet because my invention wasn't a new computer intrinsically. My invention was a new internet in reality that was defined and outlined by my global network of processors. Those processors outlined a new internet that I visualize as encircling a hypersphere embedded within a hyperspace. Each processor was my metaphor for a computer and was at a node within my new global network of 65,536 processors that was my small copy of the internet. I defined my new world's fastest computer not as a new massively parallel processing machinery, but as a new internet in reality. My theorized vision of how to invent the first supercomputer as it's known today was to harness a new internet that was a new global network of the slowest 2 raised to power 16 processors in the world. I visualized my 64 binary thousand processors as braided together and as uniformly distributed around a hypersphere that I also visualized as embedded within a 16-dimensional hyperspace. I visualized my 65,536 processors as braided together by 16 times 2 raised to power 16 short and regular email wires. My research goal was to use the Emeagwali internet to discover the fastest computer speed in the world and to invent the technology from the bowels of a huge ensemble of the slowest processors in the world. My quest for the world's fastest computer began on June 20, 1974 in Corvallis, Oregon, USA, and ended on July 4, 1989 in Los Alamos, New Mexico, USA. It was a search to find the extraordinary among the ordinary and do so by emulating the fastest processor in the world. I emulated the fastest processor by integrating the slowest processors and integrating them to invent one seamless, coherent supercomputer. That world's fastest computer is not a new computer in and of itself. It's a new internet in reality. I was the first person to witness the world's fastest computer as it's known today. That first supercomputer revealed itself across a new internet that was my new global network of the 65,536 slowest processors in the world. That was my Eureka moment because I was momentarily a mediator between God and humanity. At that moment of discovery, I was electrified because I realized that I was the first eyewitness at the then unknown field of human knowledge that's now the world's fastest computer. Until I witnessed its discovery, the first world's fastest computing across the world's slowest processors was in the realm of science fiction, not in computer science textbooks. For those reasons, it was a surreal feeling to be the first person to understand how to execute the world's fastest computation and do so across the slowest processors in the world, and realize that you will become the subject of school essays in primary and secondary schools and in revised editions of mathematics, physics, and computer science textbooks. A supercomputer is super because it harnesses up to 1 billion processors and does so to become up to 1 billion times faster than the fastest computer that is powered by one processor. My supercomputer discovery was how to code correctly and solve compute-intensive problems and solve them across millions of processors. Those processors must process in tandem and do so in reality to emulate the world's fastest computer. My scientific discovery changed the way we look at the world's fastest computer. I discovered how to develop the world's fastest computers and do so with the world's slowest processors. I discovered how to make the most with the least. The inventor creates something out of nothing. My contribution to the development of the world's most powerful supercomputers was this. On July 4, 1989, I put to rest the saying that the first world's fastest computing across the world's slowest processors and across an internet that's a global network of processors is a beautiful theory that lacks an experimental confirmation. The supercomputer is to mathematics what the telescope is to astronomy, or the microscope is to biology, or the X-ray machine is to medicine. The world's fastest computer must remain a living machinery that must be used to address the biggest questions of the 21st century. The fastest computers are used to solve the most compute-intensive problems arising in fluid dynamics. One such physics problem is global climate modeling that's executed to foresee otherwise unforeseeable long-term climate change. Another compute-intensive problem are the frontiers and the crossroad of mathematics, physics, and computer science is to foresee the spread of contagious viruses that might occur during a once-in-a-century global pandemic such as the spread of COVID-19. In my research of the 1970s and 80s, my quest was for the world's fastest computer. I wanted to discover how to solve the most compute-intensive problems in the world and how to solve them with the slowest processors in the world, but at the world's fastest computer speeds. My scientific discovery is called parallel supercomputing. In 1989, my contribution to computer science earned me the highest award in supercomputing. That award is commonly referred to as the Nobel Prize of Supercomputing. That's why I was in the news in 1989 for discovering that the fastest computing across millions of processors is indispensable and fundamental to solving the partial differential equation of calculus and for executing the most extreme scale computational fluid dynamics codes, including global climate modeling that's always a precondition to predicting long-term global warming. I discovered the fastest computing across the slowest processors, and did so at 8:15 in the morning of Tuesday, July 4, 1989, in Los Alamos, New Mexico, USA. The world's fastest computer is to the geologist or meteorologist or physicist or mathematician what the world's most powerful telescope is to the astronomer. The supercomputer changed the way we solve compute-intensive problems. In their old way, they solve compute-intensive initial boundary value problems of computational physics and solve them in sequence, or solved one problem at a time, and solved that problem within one isolated processor that wasn't a member of an ensemble of processors that were communicating and computing together and doing both as one seamless, coherent, and gigantic supercomputer. In my new way, mentioned in the June 20, 1990 issue of the Wall Street Journal, and also in cover stories of top mathematics news journals, I invented how to solve up to 1 billion initial boundary value problems of computational fluid dynamics, such as global climate modeling. My contribution to mathematics is this: I invented how to solve a billion mathematical problems at once. Within the world's most powerful supercomputer is a world of magic in which we could foresee previously unforeseeable natural events. I'm an extreme scale computational physicist who employs the laws of physics and the logic of mathematics to simulate the global motions of fluids that enshroud the Earth. I simulated those motions across the Emeagwali internet. That's a new global network of 65,536 equidistant processors surrounding the globe. That's my metaphor for the Earth. Each processor was like a dim light in a sea of darkness, but when supercomputing together as one seamless, coherent, and gigantic supercomputer, those 65,536 processors became as bright as the sun. Calculus had its origin in physics, and did so 330 years ago. Hence, new calculus could emerge when we study old physics, but do so in a new way. Calculus was invented to describe the motions of bodies. I also invented new calculus. They are called the 9 Philip Emeagwali equations. They are the most complicated equations in calculus. I invented my new calculus to describe the motions of bodies, namely crude oil, injected water, and natural gas, that were flowing up to 7.7 miles deep and flowing across an oil-producing field that's up to twice the size of the state of Anambra, Nigeria. The Emeagwali equations are to fluids flowing under the surface of the Earth, what the Schrodinger's equation is to quantum mechanics, and what Maxwell's equations are to electrodynamical phenomena. In 1989, I was in the news because I discovered how to use up to 1 billion processors to tell whether it will rain tomorrow or to determine how to extract the most crude oil and natural gas, and how to accurately nail down the exact locations of crude oil and natural gas deposits, and do so for the 65,000 producing oil fields in the world, including the 159 producing oil fields in Nigeria. My contributions to the mathematical knowledge that must be used to discover and recover crude oil and natural gas are twofold. Foremost, I was the first person to discover how to harness an ensemble of billions of processors and how to put that ensemble in the service of the petroleum industry. My discovery, called parallel supercomputing, was the cover story of top mathematics publications, including the May 1990 issue of the Siam News. The Siam News is the bi-monthly news journal of the Society for Industrial and Applied Mathematics. The Siam News is the flagship publication of the world's leading minds in mathematics. My second contribution to mathematics is this. I invented 36 partial derivative terms. I used those terms to invent the system of 9 Philip Emeagwali equations. My partial differential equations more accurately encoded the physical processes within producing oil fields. The partial differential equation is the lingua franca for computational fluid dynamics. The Emeagwali equations predetermine the motions of crude oil, injected water, and natural gas that flow up to 7.7 miles or 12.4 kilometers below the surface of the earth. An oil-producing field can be as immense as the Gawa oil field of Saudi Arabia, which measures 174 miles by 19 miles, or 280 kilometers by 30 kilometers, or 8,400 square kilometers, or almost twice the size of Anambra, Nigeria. Being able to hindcast or reforecast the motions of crude oil and natural gas that flowed up to 7.7 miles or 12.4 kilometers below the surface of the earth helps the petroleum engineer to understand how to push the most crude oil and natural gas and push them from the water injection well to the nearby crude oil and natural gas producing wells. That was the second step, which must be taken to encode the laws of physics that was discovered in prose but must be coded as a sequence of zeros and ones the processor can act on. For the third step of that conversion, I had to reformulate, or rather discretize, the 9 partial differential equations of calculus that I invented. I discretized them to convert them into an approximating system of equations of computational linear algebra. Those systems, called partial difference equations, approximated the original partial differential equations. Put differently, I used some algebraic algorithms to reformulate the 9 Philip Emeagwali equations of calculus that I invented, and to convert those 9 equations into algebraic equations, and then to transform that algebra to arithmetic or into an equivalent set of mathematical calculations and into the 65,536 codes that each of my 64 binary processors, 64 binary thousand processors, saw as a seemingly endless string of zeros and ones. In the 1970s and 80s, the idea of recording the world's fastest computer speed and doing so across the world's slowest processors was mocked, ridiculed, and rejected as a beautiful theory that will forever remain impossible to experimentally confirm. Prior to my discovery, the fastest computing across the slowest processors was dismissed as science fiction. For those reasons, it was imperative that I experimentally confirm my theory that the slowest 65,536 processors in the world could power the world's fastest computer. In science, theory and experiment sometimes contradict each other, and the experiment wins every time they clash. In my scientific research, my guiding principle was this: the logic of the compute-intensive problem should determine how the problem should be solved, not vice versa. It's only the logic, the laws of logic and physics that are sacrosanct, not the technology that must bend for the laws of logic and physics. I wasn't on the cover of top mathematics publications because I was good looking. I was on the cover of top mathematics publications because I contributed new mathematics to the existing body of mathematical knowledge. My contributions to mathematics were these: I invented a system of 9 coupled, nonlinear, time-dependent, and 3-dimensional partial differential equations beyond the frontier of calculus. The 9 Philip Emeagwali equations are for modeling the flows of crude oil, injected water, and natural gas that flow through an oil field. The 9 Philip Emeagwali equations are my contributions to mathematics, and specifically to computational subsurface geophysical fluid dynamics. Those 9 Philip Emeagwali equations govern 3-phased flows of crude oil, injected water, and natural gas that are flowing along 3 dimensions and across porous media that were both heterogeneous and anisotropic. In plain words, the properties of such porous media are different at different places and depend on the direction. I invented those 9 partial differential equations because the second law of motion described in physics textbooks can only be expressed with economy and precision if and only if I encoded that law into a system of coupled, nonlinear, and time-dependent partial differential equations. That was the reason I reformulated the second law of motion from its simple algebraic format into the most advanced expressions in calculus and into the only type of equation that was cross-listed in both the 7 most difficult problems in mathematics and in the 20 most difficult problems in computing. I also invented 9 partial difference equations that are defined at zillions upon zillions of numerical grid points that approximate the 9 partial differential equations which I invented. My 9 partial differential equations can be scribbled across one blackboard. However, coding the companion algebraic partial difference equations and coding them to solve a real-world problem, such as simulating the flow patterns across an oil-producing field that's an average of 1 mile below the surface of the earth, and that's the size of a town, and that's chopped up into millions of smaller and equal-sized mathematical problems, demanded that I code them across as many processors. Those processors were identical, coupled, and shared nothing. I maintained a one small reservoir to one slow processor mapping, which enabled me to maintain nearest neighbor nearness. That was the mathematical precondition to inventing the world's fastest computer that's powered by millions of processors. In 1989, I was in the news for providing the quote-unquote final proof that the fastest computing across the slowest processors is not science fiction. I visualized email communications across the 65,536 processors that I used to conduct my physical experiment of July 4, 1989. That experiment made the news headlines as the first world's fastest computing across ordinary processors. I had to visualize the topological positions of my processors and identify them correctly before I could accurately execute my 65,536 reservoir to processor mappings. Likewise, I visualized 65,536 processors that were equal distances apart that I imagined as etched onto my hyperspherical model of the Earth. Furthermore, I visualized my 65,536 equal fluid volumes as enshrouding my hyperspherical model of the Earth. Not only that, I visualized the laws of motion, energy, and conservation as described in physics textbooks as acting on each fluid volume. I visualized that 16-dimensional spherical model of the Earth as mapped onto the Earth, so that each of those 65,536 fluid volumes were separated by 3,000 square miles. I invented a new internet. And I did so during my quest to discover how to simulate the geophysical fluid dynamics flows of the air and water that enshrouded a globe that's a metaphor for the Earth. Along the way to the world's fastest computer, I invented how to formulate partial differential equations for the oil and gas industry correctly. I invented the 9 Philip Emeagwali equations that govern three-phased fluids flowing across porous media that were both heterogeneous and anisotropic. I did so by encoding into my partial differential equations the second law of motion of physics as described in textbooks and discovered 3 centuries and 3 decades ago. Attempting to unravel the analytical or the truest solution of a complex partial differential equation is like playing chess with God. In 1974, when I first programmed one of the world's fastest computers, the fastest computing across the slowest processors was both unspeakable and unthinkable. In the 1970s, it was easier to travel to the moon than to program an ensemble of millions of self-contained off-the-shelf processors that shared nothing and harness them as one seamless, coherent supercomputer. In the 1970s and 80s, the 25,000 vector supercomputer scientists in the world worked within the comfort of the unknown. Back then, the few parallel computer scientists in the world worked within the discomfort of their unknown and researched in the unexplored regions of extreme-scale computational physics, a field that encompasses climate modeling. Between physics and mathematics, the world's fastest computer occupied the position between the unavoidable and the impossible. In the 1970s or 80s, the fastest computing across the slowest processors only existed in the realm of science fiction and in the unexplored regions of the mathematical universe. During the 1980s, the big question in supercomputing that I addressed was how to connect the mathematical universe to the physical one, and in particular, how to connect the new internet that I visualized in the 16th dimensional hyperspace to the most compute-intensive mathematical problems that were defined in our three-dimensional physical space. In the 1970s and 80s, I felt like I was struggling to assemble a puzzle with infinite, endless pieces. At first, I thought my puzzle, with only 65,536 pieces, could solve the most compute-intensive problems in mathematics and science. I later realized that, in theory, the grand challenge problem demanded infinite pieces or number of processors as the precondition for solving the problem with mathematical exactitude. This grand challenge was the motivation that inspired my invention of how to reformulate some laws of physics and do so from prose to its equivalence in algebra, namely force equals mass times acceleration, to its equivalence in calculus, namely partial differential equations, to its equivalence in message passing codes that I executed on each processor and parallel processed across the Philip Emeagwali internet. That's a new global network of 2 raised to the power 16 processors. My breakthrough in supercomputing was possible because I reformulated the laws of conservation of momentum, mass, and energy as described in physics textbooks and reformulated them into processor codes that I adorned with processor-to-processor emails. I invented unknown algorithms or new supercomputer instructions which told each processor what to compute within itself and what to communicate to its up to 16 nearest neighboring processors. I emailed my 64 binary 1000 or 2 raised to the power 16 processor codes across my hyperglobe that I visualized as embedded within the 16th dimensional mathematical hyperspace. Furthermore, I emailed my 65,536 processor codes to and from my 2 raised to the power 16 processors. As a mathematician who is also a physicist, I understood my system of partial differential equations as a description of the set of laws of physics they encoded. For those reasons, I distinguished the description from the describe, just as you distinguish the map of Nigeria from the territory of Nigeria. A partial differential equation is different from the laws of physics it encodes, just as the description of Nigeria is different from the land of Nigeria it describes. I can fold the map of Nigeria and put it in my pocket, but I can't put Nigeria in my pocket. My discovery of July 4, 1989 set the blueprint for the world's fastest computers, now powered by up to 1 billion processors. The scientists who became famous were remembered, were the ones that were credited with achieving major paradigm shifts that changed the way we think, such as changing from the geometry of Euclid, who lived 2,300 years ago in Africa, to the 19th century non-Euclidean geometries. The first of the two non-Euclidean geometries is the elliptic geometry with positive curvature. In elliptic geometry, Euclid's parallel postulate does not hold. The second of the two non-Euclidean geometries is the hyperbolic geometry. Within the hyperbolic geometry, the sum of the angles of a triangle is always less than 180 degrees. The elliptic and hyperbolic geometries were the two major paradigm shifts which occurred within 2,300 years. Those two radical shifts fundamentally changed the way geometers think about geometry. Similarly, the world's fastest computing across the world's slowest processors is a radical shift that changed the way computer scientists think about their supercomputers. Parallel supercomputing is a fundamental shift in the way we compute, just as the theory of evolution changed the way biologists think. Supercomputing across up to 1 billion coupled processors fundamentally changed the way the most compute-intensive problems are solved, and changed it, just as the heliocentric worldview changed the geocentric worldview of astronomers who preceded Galileo Galilei. Parallel supercomputing changed large-scale computational physics, the way the modern physics of Albert Einstein changed the classical physics of Isaac Newton. At its essence, the fastest supercomputer that I discovered at 8:15 in the morning of Tuesday, July 4, 1989, was about changing from the computer that solved one problem at a time to the supercomputer of today that solves up to 1 billion problems at once, or changing to the internet of tomorrow, which is still in the realm of science fiction, that could become the planetary supercomputer of the future. Parallel supercomputing was a fundamental change of tectonic proportions that changed the way we study computer science. In their old computer science, the computer solved one problem at a time. In my new computer science, the computer solves many problems at once. A man said to his pediatrician, "Do you know Philip Emeagwali?" I wrote an inventor report on Philip Emeagwali. My daughter also wrote an inventor report on Philip Emeagwali. His pediatrician smiled and said, "I also wrote an inventor report on Philip Emeagwali. My son also wrote an inventor report on Philip Emeagwali." For the 12-year-old that is writing a school essay on inventors and their inventions, an essential question is this: What is Philip Emeagwali known for? I was the first person to discover that the slowest processors in the world could be harnessed and used to power the fastest computers in the world. That new knowledge is used to solve the most compute-intensive problems in the world. That invention is the reason the fastest computers in the world are powered by up to 10.65 million processors. I discovered how an ensemble of up to 1 binary billion processors can be married together by as many email wires and messages. A binary billion is 2 raised to power 32, or 4,294,967,296. And then use those processors to solve the most compute-intensive problems. I discovered how to fuse processors and do so to, in reality, form one coherent unit that's a never-before-seen machinery. That's the world's fastest computer that made the news headlines in 1989. That new supercomputer, which is also a new internet that I invented on July 4, 1989, is radically different from the constituent processors from which it originated. The world's fastest computer, as it's known today, originated from the slowest processors. My historic run was the first world's fastest computing across the world's slowest processors. My breakthrough occurred at 8:15 in the morning on July 4, 1989. I was its first eyewitness. For that reason, it was a visceral experience. My visceral cries drew a little crowd. People down the hall ran towards me as they heard my visceral cries for my discovery of the world's fastest computing. I cried because it was the first supercomputing that will change the lives of our descendants, and do so by permanently changing the way our descendants will look at their world's fastest computers. Each person that heard my visceral cries was puzzled by my emotional reaction to what seemed incomprehensible, namely the world's fastest computing that I executed in a new way that will forever change the way we look at the computer. My supercomputer run performed 3.1 billion calculations per second. That was a world record for July 4, 1989, that opened the door to the modern supercomputer. I used those 65,536 processors to solve a system of 24 million equations of algebra. In addition to my computing speed, the number of processors and equations were both world records. My 3 world records in speed, processor, and equations were validated by the computing and petroleum industries. The supercomputing industry now incorporates parallel processing, and the petroleum industry now purchases 1 in 10 supercomputers. Oh yes, harnessing a billion processors gives the right answer too. When I began supercomputing back on June 20, 1974 in Corvallis, Oregon, USA, the world's fastest computing across the world's slowest processors was science fiction. 15 years later, on July 4, 1989, in Los Alamos, New Mexico, USA, I discovered how to turn that science fiction to reality. For that contribution, I became the first and only person to win alone the highest award in supercomputing. The world's fastest computing, as it's executed today, was the pseudoscience of the 1980s and earlier. The turning point was my scientific breakthrough that occurred on July 4, 1989, and elevated that pseudoscience to science. How do I want to be remembered? I want to be remembered as the supercomputer inventor that connected those dots or vertices or processors, so to speak. I want to be remembered as the supercomputer discoverer that told the coherent story and discovered those internets as, in reality, coherent computers that are the fastest. The genius is the ordinary person that found the extraordinary in the ordinary. My invention of fastest computing is summed as follows. The slowest processors can cooperatively compute together to yield the fastest computation ever recorded and to solve the most compute-intensive problem ever solved. My discovery is used to combine computers into supercomputers and can be used to create a supercomputer that's an internet. In an email, a 12-year-old writing the biography of a famous inventor and his invention asked me, what is the Philip Emeagwali internet? In 1989, I was in the news because I recorded the fastest computer speed. I achieved that speed while solving the most compute-intensive problems at the crossroad where new mathematics, new physics, and new computer science intersect. Such compute-intensive problems are called the 20 grand challenges of supercomputing. On July 4, 1989, I recorded the world's fastest computer speed. And I did so while solving the most important compute-intensive problems and solving them across a new internet that was a new global network of the slowest processors in the world. That machinery that comprised of the slowest processors powering the fastest computer is called the Philip Emeagwali internet. Visualizing Philip Emeagwali's supercomputer, I visualized my supercomputer as outlined and defined by a billion points of light. Each light represented a processor. I programmed 2 raised to the power 16 off-the-shelf processors. Likewise, I visualized those processors as equal distances apart. Furthermore, I visualized those processors as etched onto the hypersurface of a globe. Not only that, I visualized that globe as embedded within a 16-dimensional hyperspace. That spherical island of processors is called the Emeagwali internet. If constructed at the most enormous scale, the Emeagwali supercomputer will be a mammoth machinery assembled from a billion off-the-shelf processors that are linked with high-speed interconnects that shuttles data and coordinates emails. The Emeagwali internet that I theorized in 1974 is shaped like a giant ball or a gigantic supercomputer that I named a hyperball. I visualized my giant ball as the world's fastest computer that occupies the footprint of a football field. My new supercomputer will cost tens of billions of dollars and could be financed by a consortium of nations. Furthermore, it will weigh as much as 1,000 school buses. Not only that, it could consume as much electricity as a state within Nigeria. My never-before-seen supercomputer could solve the most compute-intensive problems, including the complicated simulations of climate change that would be impossible to solve on a supercomputer that is powered by only one processor. I came to supercomputing not only to solve the most compute-intensive problems in science, engineering, and medicine, but also to invent a new supercomputer. I invented a supercomputer that was inspired by the bee's honeycomb, and did so by subdividing the surface of a sphere in an orderly and efficient manner. Studying bees and how they work together in their hives, as well as the efficiency they employed when constructing their honeycombs, inspired me to change the way I look at the world's fastest computers. I was the first supercomputer scientist to divide a spherical surface in a manner that mimics the efficient structure of the bee's honeycomb. I discovered that the natural efficiency implicitly encoded into how bees construct their honeycombs will be copied within a supercomputer that's powered by an internet that's a global network of up to 1 billion processors. The patterns of the interconnections of the processors within my new supercomputer were inspired by my observations of the efficiency of the bee's hexagonal honeycomb. The bee's honeycomb inspires the most efficient processor-to-processor interconnection that will make it possible to manufacture the world's fastest computer. That supercomputer will encircle a huge globe that occupies the space of a soccer field. My honeycomb-inspired supercomputer is a global network of processors that's an internet in reality. My honeycomb supercomputer will do the fastest computation with the least communication or noise. Over millions of years, the bee evolved to know that it can store the most honey with the least energy. I merely copied the blueprint for my supercomputer by reverse engineering the bee's honeycomb. In the 1970s and 80s, I didn't conduct academic research. Instead, I conducted a big science, big supercomputer research that was beyond the realm of academia. My new internet made the news headlines because it was my alternative way of looking at the supercomputer that previously only computed with one custom manufactured superfast vector processor. My alternative way of parallel processing became a fundamental change in supercomputing. That was the origin story of the first supercomputer in the world that was powered by the slowest processors in the world. In 1974, in Corvallis, Oregon, USA, I was solving large-scale systems of equations of computational linear algebra. I solved them on a serial supercomputer that was the first computer to be rated at 1 million instructions per second. That serial supercomputer represented the old paradigm of supercomputing. In serial supercomputing, I programmed one scalar processor, the equivalence of one computer. I visualized that one scalar processor to be on a globe in the 0th mathematical dimension. And I topologically followed the 64 binary 1,000 vertices and the 1 binary million bidirectional edges of the hypercube in the 16th dimension. I visualized them as making up a new internet that tightly circumscribed a globe with its processors and wires, and encircled that globe as a new global network of processors. I also visualized that globe in the 16th mathematical dimension. I grew in my mathematical maturity and scientific and computing expertise during the 50 years following 1974 that I lived and worked in Corvallis, Oregon, Washington, District of Columbia, Baltimore, Silver Spring, and College Park, Maryland, Casper and Laramie, Wyoming, and Minneapolis, Minnesota. I grew along 16 mutually perpendicular directions. I was the first supercomputer scientist to grow into the new billion processor paradigm of the fastest computing across a gigantic ensemble of processors. I visualized these processors as uniformly encircling a globe and as circumscribing it as a new internet that's a small copy of the internet. My new billion processor paradigm for supercomputing made the news headlines because I was the first person to record the fastest computer speed and do so across that new internet. It was at 8:15 in the morning of July 4, 1989, in Los Alamos, New Mexico, USA, that I discovered parallel supercomputing and discovered how to record the fastest computer speeds across an ensemble of 2 raised to power 16 processors. I was the first person to recognize that network of processors as a new internet that tightly encircled a globe and circumscribes it within the metaphorical 16th dimension. So over my first 16 years, from Corvallis, Oregon, to Washington, District of Columbia, to College Park, Maryland, to Laramie, Wyoming, to Los Alamos, New Mexico, my supercomputing changed from the zeroth or a mere point to the 16th dimension that was represented by 2 raised to power 16 or 65,536 equidistant points that I visualized as having a 1-point-to-1 processor correspondence. I also visualized those processors as evenly distributed across the hypersurface of a hypersphere. That was my topological metaphor for the Philip Emeagwali internet. In summary, I theorized and experimentally discovered that new internet. The supercomputer market is $45 billion a year. That's like giving $1,000 a year to every man, woman, and child who can speak the Igbo language. Since 1989, I'm the subject of inventor reports in schools across the USA, UK, and Canada. I'm studied in schools because I discovered that the modern supercomputer should be powered by up to 1 billion processors. That invention is the new knowledge that powers the world's fastest computers. In 1989, I was in the news because I discovered how to solve the most compute-intensive mathematical problems such as initial boundary value problems that were governed by a system of coupled partial differential equations, and in particular, those arising in planetary scale fluid dynamics. Such equations contextualized and encoded some laws in physics, including the second law of motion. Such partial differential equations capture in a few succinct terms some of the most ubiquitous features of the air and water flowing across the surface of the earth, including the atmosphere and oceans, and the crude oil, injected water, and natural gas flowing across highly anisotropic and heterogeneous producing oil fields that were up to 7.7 miles or 12.4 kilometers below the surface of the earth, and that are the sizes of a town. The size of the Prudhoe Bay oil field on Alaska's North Slope is 213,543 acres. The Prudhoe Bay is the largest oil field in North America. The Gawa oil field of Saudi Arabia measures 280 kilometers by 30 kilometers, or 174 miles by 19 miles. The Gawa field is the largest oil field in the world. In an email, a 15-year-old writing the biography of a famous mathematician and his contributions to mathematics asked me, how is mathematics used in supercomputing? Calculus is the most powerful technique in mathematics. The poster boy of the partial differential equation of calculus is the system of equations that encoded the second law of motion in physics textbooks. In theory, mathematical predictions that are based upon the partial differential equation should be as reliable as a hammer. In practice, it's a different story. Therefore, it's impossible to predict the weather with certainty and forecast it 30 days in advance. Without high-performance, massively parallel supercomputing, the solution of the most compute-intensive initial boundary value problems, such as simulating long-term climate change, will be as approximate as a sketch instead of as exact as a photograph. That solution of that mathematical problem is a map called the vector field of the direction, size, and temperature of the air or moisture at every position within the Earth's atmosphere and at every later date. The need to simulate accurately the internal dynamics of flowing fluids, called fluid dynamics, is the reason 90% of the cycles of the world's fastest computers are consumed by applied mathematicians called computational fluid dynamicists. Large-scale computing is the reason the fastest supercomputers are used to study and understand long-term global warming. In an email, a 12-year-old writing her biographical essay on a famous inventor and his invention asked me, how did you invent the Philip Emeagwali internet? I explained to her that my invention was inspired by my thinking about the earth and global warming. I progressively made my invention during the 16 years following June 20, 1974. I started my research in Corvallis, Oregon, and I continued my supercomputing in Washington, District of Columbia, College Park, Maryland, Laramie, Wyoming, and Los Alamos, New Mexico. I began the invention of the Philip Emeagwali supercomputer by imagining the Earth as shrunk to the size of an apple. The size of the skin of that apple represents the habitable area of the Earth. That skin-thick volume consists of fluids such as the atmosphere, rivers, lakes, and oceans. And up to 7.7 miles below that skin-thick volume, we have fluids such as crude oil, natural gas, and air that flow through the crevices and voids under the surface of the Earth. One of the 20 most compute-intensive problems in physics was to simulate global warming across millions of processors under the hood of the world's fastest computer, and do so to execute computational fluid dynamics codes at the world's fastest computer speeds. Likewise, to foresee the motions and the directions of the fluids that enshroud heavenly bodies, such as the geophysical and astrophysical fluid dynamics around planets in our solar system, including weather forecasts around the Earth. The Earth's atmosphere is 62 miles or 100 kilometers above its surface. Comparing the depth of the Earth's atmosphere to its diameter of 7,900 miles or 12,700 kilometers, we realize that the atmosphere is 127 times thinner than the Earth. The atmosphere compared to the Earth is thinner than the skin of the apple compared to the apple. In 1,000 years, I see the internet to be an electronic cloth that enshrouds the Earth and does so just as the skin of the apple covers the apple. I began my technological quest for the Philip Emeagwali internet by visualizing how to solve compute-intensive mathematical problems. Such difficult problems arise in large-scale computational physics. I described and defined my physics problem on and across 65,536 or 2 raised to power 16 blackboards. Each blackboard contained the corresponding initial boundary value problem of mathematical physics. Those initial boundary value problems can't be analytically solved on those 64 binary thousand blackboards. Hence, I computed their 65,536 answers. And I did so across my ensemble of 65,536 motherboards. Early on, I was mindful of the fact that I must relate my discovery of the first world's fastest computing across the world's slowest processors and use it to solve the biggest mathematical challenges arising in science, engineering, and medicine. I discovered how to compute at the fastest speeds in the world and do so 65,536 times faster and do so across a new internet. I'm often asked to describe how I visualized the Philip Emeagwali internet. I visualized that new internet as a new global network of 65,536 processors. I visualized the Philip Emeagwali internet as etched onto the hypersurface of a globe that I visualized in the 16th dimensional hyperspace. I also visualized 65,536 equal-sized atmospheres each projected from the surface of the Earth to the uppermost atmosphere, or 62 miles or 100 kilometers above the surface of the Earth. My tessellated atmosphere is a concentric globe that I defined in the third dimension. I knew it's important that I relate the two internets that I invented. My first internet was only theorized and constructively reduced to practice. In reality, the Philip Emeagwali internet was a supercomputer. My second internet was experimentally reduced to practice as the world's fastest computer. My discovery that the first supercomputer, as it's known today, can be developed with the slowest processors made the news headlines shortly after I discovered it on the 4th of July, 1989 in Los Alamos, New Mexico, USA. I'm often asked, what is the Philip Emeagwali internet? The Philip Emeagwali internet is a spherical island of processors that encircles a concentric globe that represents the habitable atmosphere where global warming occurs. My scientific discovery, which occurred on the 4th of July 1989, encompasses how to forecast global warming and how to do so more accurately, and how to forecast it across my new internet that's a new global network of off-the-shelf processors. My processors were identical, equal distances apart, and shared nothing, but were in dialogue with each other. That discovery is my contribution to the greater understanding of the relationship between the supercomputer and the internet. I saw none of my 64 binary thousand or 65,536 processors with my naked eyes. However, I saw each processor with my mathematical mind. That abstraction enabled me to geometrically visualize them as an internet and do so with a one processor to one vertex correspondence. Likewise, do so at the 65,536 or 2 raised to the power 16 vertices of a hypercube in the 16th dimension. I also visualized that hypercube as tightly circumscribed by a hypersphere that represented a globe in the 16th dimensional hyperspace. My quest was for the first supercomputer that will be powered by a large ensemble of off-the-shelf processors. During the 16 years of supercomputing research that followed June 20, 1974 in Corvallis, Oregon, USA, my most important questions were always these. How can I record the world's fastest speed in computing? And how do I use the fastest computer speeds across ordinary processors to solve the most compute-intensive problems? My contributions to computational mathematics were these. In 1989, I was in the news for discovering how to solve the most compute-intensive problems. Such difficult mathematical problems arise during oil recovery or global warming predictions and other scenarios in computational fluid dynamics. Such problems are posed and solved as initial boundary value problems of mathematics and physics. In 1989, I discovered a different supercomputing that created a different computer science. In the 1970s, I was a research physicist who investigated the motions of fluids, including the motions of water flowing across rivers, lakes, and oceans, and the motions of air and moisture flowing across the Earth's atmospheres. I mathematically and computationally investigated how to predict such motions. I described my new field of study as large-scale computational fluid dynamics modeling across a global network of millions of processors. I'm a black physicist that's invincible in a white space. In the 1980s, I was underestimated and dismissed as unqualified. Far more importantly, I was dismissed by those who were unqualified. Yet, I'm the only physicist that's qualified to deliver lectures and distribute them across 1,000 podcasts and YouTube videos. Each lecture was on my contributions to the solution of the hardest problem in computational physics. During the 15 years following June 20, 1974, in Corvallis, Oregon, I grew my expertise from experimental physics to astrophysics, to geophysics, to mathematical physics, to large-scale computational physics. I grew my expertise across a new internet that's my new global network of off-the-shelf processors. My processors were equal distances apart from each other, and we are identical to each other. That contribution to the invention of the first supercomputer, as it's known today, put me in the news headlines. A question in school essays on famous physicists and their discoveries is this: what is the contribution of Philip Emeagwali to physics? In 1989, I was in the news headlines because I discovered how to harness millions of the slowest processors in the world and across an internet that's a global network of those processors. Furthermore, I discovered how to use them as one seamless, coherent, and gigantic unit that's the world's fastest computer. The computer is an inch away from the number 0 or 1, and the supercomputer is a mile away from anything written in prose. I had to reformulate the second law of motion described in physics textbooks and discovered 330 years ago and discovered in prose into algebra, or F equals MA. I invented algebraic algorithms that I used to encode that law into a code that the computer can then translate into a sequence of zeros and ones. My conversion from prose to zeros and ones was executed in 3 steps. First, the second law of motion, discovered 3 centuries and 3 decades ago, was formulated as an algebraic formula that is well known as F equals MA. That formula is the algebraic acronym for force equals mass times acceleration. Second, F equals MA was reformulated in the 1820s and from algebra to calculus, or a system of coupled nonlinear partial differential equations. The 9 Philip Emeagwali equations that I invented were new partial differential equations. My equations could be used by the petroleum industry and used to simulate multi-phase fluids flowing across porous media that are heterogeneous and anisotropic. My equations could be used to map the flow patterns within an oil-producing field. That petroleum supercomputer code, called a reservoir simulator, is used to recover crude oil and natural gas. My contributions to the mathematical knowledge that is used to discover and recover crude oil and natural gas are twofold. Foremost, I was the first person to discover how to harness an ensemble of millions of processors. I discovered how to put that ensemble in the service of the petroleum industry. My discovery that the first supercomputer, as it's known today, must be powered by off-the-shelf processors was the cover story of top mathematics publications, including the May 1990 issue of the Siam News, that was the bi-monthly news journal of the Society for Industrial and Applied Mathematics. The Siam News is the most important publication that is read by the world's leading mathematicians. My second contribution to mathematics is this. I invented 36 partial derivative terms, and I used those mathematical terms to also invent the system of 9 Philip Emeagwali equations that more accurately represents the physical processes within producing oil fields. Those processes predetermine the notions of crude oil, injected water, and natural gas that flow up to 7.7 miles or 12.4 kilometers below the surface of the earth. An oil-producing field can be as large as the Gawa oil field of Saudi Arabia, which measures 174 miles by 19 miles, or 280 kilometers by 30 kilometers, or 8,400 square kilometers, or almost twice the size of Anambra, that is my state of origin in Nigeria. Being able to hindcast or reforecast the motions of the crude oil and natural gas which flow below the surface of the earth helps the petroleum engineer to understand how to push the most crude oil and natural gas and push them from the water injection well to the nearby crude oil and natural gas producing wells. That was the second step that must be taken to encode the laws of physics discovered in prose, but must be encoded, but must be coded as the sequence of zeros and ones that the processor can act on. For the third step of that conversion, I had to reformulate, or rather discretize, the 9 partial differential equations of calculus that I invented. I discretized them to convert them into an approximating system of equations of computational linear algebra. Those systems, called partial difference equations, approximated the originating partial differential equations. I used algebraic algorithms called finite difference discretizations to reformulate the 9 Philip Emeagwali equations of calculus that I invented, and to convert my 9 equations into algebraic equations, and then to further transform that algebra to arithmetic or into an equivalent set of mathematical calculations and into the 65,536 codes that each of my 64 binary thousand processors saw as a seemingly endless string of zeros and ones. In the 1970s and 80s, My unproven idea of the first world's fastest computing across the world's slowest processors was mocked, ridiculed, and rejected as a beautiful theory that demanded an experimental confirmation until my discovery of parallel processing on July 4, 1989. Supercomputing, as it's executed today, was dismissed as science fiction. For those reasons, it was imperative that I experimentally confirm my theory of the fastest computing across the slowest processors. In science, theory and experiment sometimes contradict each other, and the experiment wins every time they clash. For me, the 1970s was the decade for the fermentation of my theory that the world's fastest computer can be defined and manufactured across millions of processors that shared nothing. The 1980s was the decade that I experimentally confirmed my theory of the fastest computing across the slowest processors. I had to let those 2 decades go between before I figured out how the new internet, that was a new global network of 64,900,000 off-the-shelf processors, that each operated its operating system, and how that new internet could be harnessed as an instrument of large-scale computational physics and used to solve the most compute-intensive problems known as the 20 grand challenges of supercomputing. The 3 inventions that led to the fastest computer were the transistor, invented in 1947, the integrated circuit, invented 11 years later in 1958, and parallel supercomputing, invented 31 years later in 1989. Without the invention of the transistor, the computer will be slow, will often break down, will be the size of a building, and will cost $100 million each. The grand challenge of inventing parallel supercomputing resided at the frontiers of knowledge of physics, calculus, and algebra, rather than at the frontiers of computer science. For instance, the laws of physics must be encoded into calculus and be discretized into algebra and used to forecast the speeds and directions of air and moisture flowing over the earth, or to forecast the weather. The laws of physics must be used to hindcast or reforecast the speeds and directions of the crude oil, injected water, and natural gas that were flowing up to 7.7 miles or 12.4 kilometers below the surface of the earth, and flowing across an area under the surface of the earth that's often almost twice the size of the state of Anambra, Nigeria. 1 in 10 supercomputers were bought and used to foresee the motions of crude oil and natural gas that were flowing across the 65,000 producing oil fields of the world, including the 159 oil fields of Nigeria. After 50 years of supercomputing, an audience was taken aback when I gave it a 4-hour lecture, and did so without notes. I understood supercomputing more than I understand my wife. After all, I've only been married for 40 years, but I was married to the supercomputer for nearly 50 years. For half a century, it was my job to know the supercomputer inside and out. The supercomputer is the other woman in my life. According to Google searches, I know the supercomputer, and the supercomputer knows Philip Emeagwali. My contribution to computer science is this: On the 4th of July 1989, I discovered that the slowest processors could be programmed to emulate one supercomputer or one seamless, coherent, and gigantic machinery that's a new supercomputer in reality. Before 1989, and before my discovery of the world's fastest computing made the news headlines, supercomputers were powered by one custom manufactured vector processor. In 1989, I discovered that the world's most powerful supercomputer could be powered by the slowest 2 raised to power 16 or 64 binary thousand processors. Those 65,536 slowest processors in the world must be identical, be coupled, and share nothing. Each processor must operate its operating system. My invention made the news headlines because it was a new internet that was a new supercomputer in reality. My invention was a high-performance supercomputing machinery. That supercomputer invention of how to solve problems across processors is now used to solve the most compute-intensive mathematical problems known as the 20 most difficult problems that we are at the crossroad where the frontiers of mathematics, physics, and computing intersect. The poster boy of the hardest problems is using the supercomputer to forecast the weather above the surface of the earth. The poster girl of compute-intensive problems is harnessing the millions of processors under the hood of the world's fastest computer and using them to hindcast or reforecast the quote-unquote weather within an oil-producing field that's up to 7.7 miles or 12.4 kilometers deep and flowing across an area up to twice the size of Anambra, Nigeria. Looking back, you may ask, what training and knowledge does it take to be the first person to solve the most compute-intensive problems at the crossroad where mathematics, physics, and computer science met? My answer is this. Only a foremost expert in mathematics, physics, and computer science can solve the toughest multidisciplinary problems in extreme-scale computational science. In 1989, there were 25,000 supercomputer scientists logged onto all the world's vector supercomputers. But I was the only person in the world that was logged on full-time on potential supercomputers that were powered by the slowest processors in the world. If those 25,000 vector supercomputer scientists had possessed the multidisciplinary knowledge that I possessed in 1989, they would have solved the hardest problems that addressed the biggest challenges, such as the computational fluid dynamics that governs the spread of COVID-19 within New York City trains that pack passengers like sardines. And he or she would have posted as podcasts and YouTube videos his or her contributions to high-performance computing. I posted as podcasts and YouTube videos 1,000 closed caption videos that described my contributions to mathematics, physics, and computer science. My discovery that the world's fastest computer can be built from the slowest processors in the world was the reason I was in the news. In 1989, I was described as the lone wolf at the farthest frontier of supercomputing. Processing across the slowest processors was the technology that I harnessed and used to execute the world's fastest computer speed. I reached that milestone in the history of technology and did so back at 8:15 in the morning of the 4th of July 1989 in Los Alamos, New Mexico, USA. The June 20, 1990 issue of the Wall Street Journal recorded my supercomputer breakthrough. The partial differential equation is the natural dialect of computational fluid dynamics. The 9 Philip Emeagwali equations enabled me to see forces, otherwise invincible, and describe the motions of crude oil, injected water, and natural gas that would be otherwise indescribable. The mathematical structure or the partial derivative terms of the governing equations for fluids flowing across a porous medium is like that for fluids flowing across a non-porous medium, including the air and moisture that were flowing across the Earth's atmosphere. I discovered that for the system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations of mathematical physics that governs flowing fluids, that the meteorologist and the geologist were solving similar puzzles, but only the meteorologist solved the puzzle correctly. My contribution to computer science is this. I was the first supercomputer scientist to visualize millions of an ensemble of off-the-shelf processors and to comprehend that ensemble as uniformly encircling the globe that I also imagined in a 16-dimensional hyperspace and pictured as encircling that globe in the way the internet encircles the Earth. That new machine is called the Emeagwali machine or the Emeagwali supercomputer. The Emeagwali supercomputer that encircles the globe wasn't a new computer intrinsically, but was a new internet in reality. In the Emeagwali supercomputer, I pictured the arithmetical calculations that arise when solving the most compute-intensive problems as being executed across a small copy of the internet. The only proof you are the first person to execute the world's fastest computing across the world's slowest processors is to first do it and win the Nobel Prize of Supercomputing for your world's fastest computing, and then post a complete series of podcasts and YouTube videos on how we discovered supercomputing as it's executed today. Inventing the world's fastest computer is not a contribution to knowledge that you study for. The invention of a never-before-seen computer that records unrecorded speeds is the creation or the constructive reduction to practice of a machinery that didn't exist. Hence, the act of recording the fastest computer speed can be studied for and was never achieved within the campus of any institution of learning. How could I have been taught a never-before-seen supercomputer? How could I have been taught something that wasn't known and something that I was the first person to know? That's like attempting to remember your life before the day you were born or conceived. I was the first person to discover that the world's fastest computer should be powered by up to 1 billion coupled processors, therefore attempting to teach me my invention of parallel supercomputing was as impossible as undertaking to teach the first pilot how to fly. In retrospect, and as a black inventor, I wasn't allowed to be the inventor of my invention. A few years ago, some American academics falsely claimed to have invented the new global network of processors That's a new internet and also a new supercomputer. I invented that new internet alone. In the 1980s, those academics who had never seen a supercomputer before falsely claimed to have taught me how I discovered the world's fastest computation. But my question to them was this: who taught you the world's fastest computation? I recorded the fastest computer speed in Los Alamos, New Mexico, USA. And I did so outside an institution of learning. I did so on July 4, 1989. I didn't record the fastest computer speed in Corvallis, Oregon, USA, even though I began programming the fastest computers 15 years earlier in Corvallis and in an institution of learning. The precondition for a lone supercomputer scientist to record the fastest computer speed and record it with a technology then considered impossible is that he or she was a polymath that was beyond the boundaries of knowledge of mathematics, physics, and computer science. No formula guarantees the invention of a new computer. There is no research plan that will guarantee the invention of a new supercomputer that's a million times faster than the world's most powerful supercomputer. I programmed the state-of-the-art supercomputers on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, USA. For the following decade and a half, I programmed serial number 1 parallel supercomputers. Serial number 0 supercomputers were air-gapped and became an island of processors that were physically isolated from unsecured networks. Serial number 0 supercomputers weren't directly connected to other front-end computers. Serial number 0 supercomputers were used for simulations of nuclear explosions. The most powerful supercomputer in the world was used to simulate the explosive power of nuclear bombs that most satisfactorily agree with the actual nuclear explosions. The simulations of nuclear explosions are governed by a system of time-dependent, three-dimensional, and nonlinear partial differential equations. In such partial differential equations with nonlinear or troublesome terms, the change in the output or in the answers is not proportional to the change in the input or in the initial and boundary conditions. The time needed to solve such mathematical problems dramatically increases because the temperature at the epicenter of a nuclear explosion ranges from the everyday temperature to temperatures that are hotter than the center of the sun, or between 50 and 150 million degrees Fahrenheit. The dependent variables of those partial differential equations describe the fission of nuclear fuel by neutrons and describe the spreading of the resulting neutrons. Fission is the release of energy during a nuclear reaction. Fission occurs when a heavy nucleus spontaneously splits or impacts another particle. The dependent variables of those partial differential equations also describe the release of energy and transferring energy through the highly heated matter. My contributions to computer science changed the way we look at the world's fastest computers. On the 4th of July 1989, I became the first person to figure out how to harness the potential supercomputer power of an ensemble of the slowest processors in the world. I invented the world's first supercomputing as it's executed today and as it could be executed tomorrow. After that discovery, I was in the news because I discovered how the slowest processors could be utilized to answer the unavoidable question of the new computer science. That big question was this: for a small price and many processors, what is the upper limit on the speed of the fastest computer? My invention made the news headlines because it was the biggest measurable contribution in both speed and speed up in the history of computer science. It was the most significant fundamental change in supercomputing since the automatic programmable supercomputer was invented 43 years earlier, or in 1946. I was in the news because I computed at a supercomputer speed that was considered impossible to attain. Not only that, I was in the news because I redefined what speeds are possible in supercomputing. Furthermore, I was in the news because I discovered a fundamental change in the way we look at every supercomputer. In the history of computing, a fundamental change occurs once in a century. My fundamental change was from serial computing within one processor to supercomputing across my new internet, that's a new global network of up to 1 billion coupled processors. Those processors were identical and shared nothing, but were in dialogue with each other. The first world's fastest computing across a globe, or planet Earth, was speculated and entered into the realm of science fiction, and did so when it was first published on February 1, 1922. I was in the news because breaking that supercomputer speed increase barrier was computing's equivalent of being the first person to summit the peak of Mount Everest. My discovery of the world's fastest computing created a new supercomputer science and made it possible for the next generation of mathematicians to solve their most difficult problems and do so across millions of processors. My discovery of the world's fastest computing that occurred on the 4th of July 1989 had the most disruptive impact in the fields of applied mathematics and computational physics. Parallel computing was a disruptive supercomputer science. The computer speed increases obtained via parallel supercomputing provided the bedrock certainty that the laws of motion provided for the physicist. Thank you. I'm Philip Emeagwali. Thank you very much. Thank you.
Insightful and brilliant lecture.
Thank you.